Hello everybody, I'm Ruben, a recent maths graduate from Cambridge. I tutor maths in my spare time and I've given mock Cambridge maths interviews for several years now. I'm excited to be making a video. In this video I'll be going through one of my favourite maths interview questions. I hope it's useful to you all. And do let me know if this is useful so that I know if making more of these would be of interest. So firstly, what's the first part of this question? It's going to be to sketch this graph. Y equals natural log of x over x. Now feel free to pause the video and do this and then come back for a solution. Great, so y equals natural log of x over x. What is the first thing to do for such a graph? Now I'm sure you're familiar with the components of this, and this really isn't that difficult of a graph to sketch, but what's the first thing to do? Well, the first thing is to see what are the values of x for which to sketch this. Now you know that natural log of x is defined for x greater than 0, and you know that x, well, is defined for all real x. So certainly this function is going to be defined for x greater than 0 because it has a natural log. Next thing to do typically is to look at the roots of this. Where is it 0? So we can number the steps actually to make this more generalizable. Step 1, 2. What are the roots? Well, y is equal to 0 if and only if the numerator here is equal to 0, log x is equal to 0, which is x equal to 1 from the standard properties of logarithms. Great, that's simple enough roots. Now the next step is really how to get a lot of free wins in these type of questions, and is to look at the asymptotes as early as possible, because typically people go and start differentiating once and twice and get carried away, but really it's much better to take a moment to study the global properties of this graph. So what happens, for example, when x approaches infinity, right? Well, when x approaches infinity, we know, or at least we should know, that log x grows slower than x. That can be seen from just considering the graph, although of course you'd need to know that the graph looks like this, which you should, x and log x, and log x over x is going to tend to 0 because log x is growing way slower than x. So as x approaches infinity, y tends to 0, and where does it tend to 0? Top or bottom? Well, everything here is going to be positive, so it tends to 0 from the top. And these type of considerations are very useful for when you actually try and connect your graph up. Again, this is a very simple case, but it's important to think about that in general. Now, the other edge of the domain, if you like, is x equals 0. What happens as x approaches 0? And indeed, it's x approaching 0 from the right again, because x is positive as the domain. Well, you know certainly that natural log of x is going to minus infinity, and that x is going to 0 from the right. So log x over natural log of x over x is a huge negative number divided by a tiny number, so it's going to be an even bigger negative number. So y is going to minus infinity, definitely. Now, we actually currently have all the information to know what the shape of the graph is, because if we just draw what we know so far, we know that as x approaches 0, the graph is going to be down here, minus infinity. We know that as x approaches infinity, the graph is going to be somewhere here, 0, but from the top. And we know that the graph crosses the x-axis at 1. Now, if you have some intuition as to how these functions behave, you would think that the way to join up all this information is to just have a graph that looks like this, goes up somewhere here and then goes back down. That would be correct, and indeed we'll see that's how the graph looks, but in general from here it might go up and down like this before it goes back down. Now obviously this is a very simple function and that's certainly not happening, but that's just a word of warning. How can we investigate this more rigorously? Of course, we do need to take the derivative now, and you might be somewhat thinking that I'm averse to taking the derivative because I encourage you to look at the asymptotes first, but in general, at least the first derivative you will consider, very rarely the second derivative in these type of graph sketch questions. So what's happening with the derivative? Natural log of x over x. The derivative of that is going to be, so we'll use the quotient rule, 1 over x on the top times x minus the derivative as x is 1 times log x over x squared is equal to 1 minus log x over x squared. Where's this 0 to find the turning points? Well, this is 0 if and only if this numerator here is 0, i.e. if log of x is equal to 1, i.e. if x is equal to e. And there's only one turning point, and we know that the graph looks like this. So we actually don't need to consider any further derivatives or arguments about if it's a maximum or a minimum, because we know at x equals e, this here is going to be, well, there's going to be a point here, it's going to be positive. We know that just because it's log e over e. There's a point here, and we just know that it's going to be a maximum, and that the graph is going to look like that. That is how the graph looks. Maybe should just sketch that better, but just connecting all the information we have, something like that. Well, that's the maximum point. And if you really do want to see that this is a maximum, do not take the second derivative. Rather look at the sign of the first derivative. So we can see the first derivative was 1 minus log x over x squared. What's happening at x less than e? Well, 1 minus log x. Log x is going to be greater, less than 1, sorry. So that means the derivative is going to be positive. And when x is greater than e, log x is going to be more than 1, so the derivative is going to be negative, which is indeed consistent with this graph we've got here. We do precisely have a positive slope before x reaches e and a negative slope after that. So that is the graph. That's I'd say basic graph sketch, but the principles here in particular, looking at the asymptotes early and not rushing to take the second derivative to work out to maximum or minimum, those are key principles. And just for completion's sake, we know if we want to label the coordinates of this point extensive fully, it's going to be e. We have here log e over e, that's the y-intercept, which is 1 over e. Great. Now there's a second part to this question, which I'd encourage you to pause again to think about. And that is, hence, using this graph, work out which is greater of these two numbers, e to the pi or pi to the e. Now, feel free to pause and come back for a walkthrough. Great, so e to the pi and pi to the e. This is a hence question, so the last thing we did here was work out the graph, so it's got to be something to do with the graph. Okay. Well, e to the pi and pi to the e, the only thing that's actually the same between these two problems is that e appears in both. We have e here, and that is a key point on the graph. That's a turning point. And the other number of interest is clearly pi, right? We know that pi is greater than e, or at least that is something that you should know. Pi is 3.14, e is 2.718. So if we just plot this here, or look at pi on this graph, it's going to be to the right of e. And now we want to think about what are some inequalities that we can come up with, apart from the most obvious pi greater than e. Well, we know e is the maximum point of this graph, indeed the global maximum. So what can we compare? We can compare the y values. If we look at the y values here, that's 1 over e, and for pi, that's ln pi over pi. That's great. That is exactly great. So if we look at those values, we can construct an inequality. So if we go down here again, we know that we now know that 1 over e is greater than ln pi over pi. And if we just work on this a little bit, we have pi is greater than e to the ln pi. And we have, using the rules of logarithms, pi is greater than ln pi to the e. And now if we apply the exponential function to both sides, we have e to the pi is greater than e to the ln pi over e. Indeed, these are inverses of one another, e and log. So we have e to the pi is greater than pi to the e. That's great. That is the answer, but we made a, well, maybe, I hope you didn't, but we made a small jump in logic here, which is we applied the exponential function to both sides, and we preserved the inequality. Of course, if it was an equality, then we can do that without a problem, but with inequalities we always need to be careful. Why could we apply the exponential function to both sides and preserve the inequality like that? Well, that's because the exponential is an increasing function. If you've got two values here, a and b, you're going to know that their y values obey the same relation. If a less than b, then e to the b less than is greater than e to the a. And you already know a classic example where this would not be the case, and that's when you add a minus sign. And the reason for that is because y equals minus x is a decreasing function. It's not increasing. So a key general principle is if you have x greater than y, you only have f of x greater than f of y if f is increasing. Now, again, this is an overly simple example to demonstrate that fact. However, that is a key principle that you should always think about when you're working with inequalities and applying functions to both sides. And of course, that is the solution here. And you might not have known you might not have known this particular relation, or even if you did, this is a very neat way of proving it. So that's it for this question. I hope that was useful and enjoyable to you. This was, as I said again, as I said before, this is not one of the most difficult questions. It's short and sweet. But do drop a comment to let me know what you thought. I'm open to making more such videos. Like and share the video, I guess, and subscribe so that I can make these and not just make them for my own viewing. And have a great day from me. Thanks.